Hey, everybody. Welcome to AP Chemistry today. I hope you're all doing well. Again, just a couple of things before we get started on Note Sheet 1.5. Homework Topic 1, which is titled HW Unit 1, Topic 1. That's due tonight by midnight on its learning. I sent you all an email this morning saying that it was closing at the wrong time, right? I fixed that. So if you didn't submit it yet, you still absolutely 100% can. All I need you to do for that is take a picture of your sheet and then submit it to the assignment that I have set up for that HW Unit 1, Topic 1. Okay, so that's due by midnight tonight if you could. The other thing is the AP Classroom multiple choice assignment. There's been some issues with that. There's a couple people that are like stuck and can't access the quiz. I haven't quite figured out what's going on with that just yet. And the other thing is, I think there's one single person who has not signed up for AP Classroom yet. I could cross-reference it and figure it out who it is. I just hopefully if you're out there and you know it's you, I would recommend doing that because I am going to have assignments on there all year long. But anyway, so the multiple choice assignment on AP Classroom, if I'm able to figure out how to fix it for a couple people, hopefully I can close it down by tomorrow night at midnight. If not, I'll reopen it one more time. So if you're a person who cannot access that stuff, don't freak out. It'll hopefully be, I'm hoping that I can get you access to it in the near future. I just got to get to the bottom of what's causing it to not work for a couple students. So anyway, today, apart from the homework stuff, and by the way, if you did notice in the plans, homework topic 2, HW Unit 1, topic 2, that's going to be due Thursday by midnight. Okay, so please be aware of that if you finish topic 1 or you've finished topic 1, please start taking a peek at topic 2 and chipping away at that, and that'll be due Thursday night. There's one thing on topic 2 that I haven't quite taught you yet. I'll talk about that tomorrow, I guess, because I got to make sure I do it before the Thursday deadline. But there's one problem on there that you'll be like, wait, we never talked about any of this yet. And when you get to that point, feel free to skip it, or you can shoot me an email or come stop into my office hours. But just a side note before you freak out on me. Yeah, all right. I think that's all I got for beginning of class stuff. As I'm going along today, please feel free to, again, interject if there's something that I say or something's confusing or I'm not quite explaining something very well. Please stop me. I know that feels like it might be awkward and it feels like you don't want to be the one to halt class, but in all honesty, I need somebody to stop me if I'm just plowing forward and leaving everyone in the dust, okay? Because today can be a smidge confusing. I'll preface that. Please hang with me. I promise that slowly but surely what I'm talking about today will make sense. It really, really will. I promise you. It's just that as of day one of this stuff, it sometimes hits a little hard. So brace yourself, hang in there. I'll go slow. I'll explain things hopefully 3-4 times and have it hopefully click a little bit today. But if it doesn't quite click today, don't worry. We're going to work on this same note sheet, this 1.5 stuff for the next 3 days, in all honesty. So this is a big, this is kind of the crux of this first unit. All right. So hang with me. All right, let's get started. Oh, and by the way, I think everyone has almost done it, but if you haven't typed in here in the chat, please do so I don't mark you absent. All right, so today's topic, 1.5, atomic structure and electron configuration. Today's learning objective, we want to represent the electron configuration of an element or ions of an element using the Aufbau principle, okay? Aufbau, that's a dead white guy's last name, okay? So he has a principle related to our topic today. We'll talk about it in today's lesson, but if you're curious what the heck that word means or where that came from, Aufbau is the last name of a dead white guy. All right, we'll start here. What are the 3 subatomic particles that make up atoms? Okay, and if somebody would, it's nice to hear a voice every now and then as opposed to silence. Somebody want to unmute themselves and give me these 3 because I hope you know what the 3 subatomic particles are.
Proton, neutron, electron.
I have no clue who that was, but that was very emphatic, and I appreciate your excitement for chemistry. All right, yeah, protons, neutrons, and electrons. Okay, Okay, old news, right? That's nothing new. That's 100% not even last year's stuff. That's like probably 6th grade science stuff, or maybe even earlier than that, okay? But yeah, these are our 3 subatomic particles. So with that, we've kind of given you a way of organizing these, or in other words, we've given you a general outline of how atoms are arranged, right? So how are these things arranged? We have a nucleus, okay? And in that nucleus, we have the protons and the neutrons. Around the outside, okay, outside, okay, let's try that again. Outside are the electrons. And normally what we taught you, or what you heard or what you were told earlier in your education, was that these electrons are in shells or clouds. Electron shell, electron cloud. You may have heard those terms. So around the outside are the electrons, and they are in shells, and I'll put that in quotes, or clouds, however you want to say that. Those terms aren't great, because when I say shell and I say cloud, I'm not talking about seashells, and I'm not talking about clouds that you see outside, right? It's just kind of a word that describes where the electrons are. They're not great. Good news, we're never going to use them again, but this is probably or potentially what you've heard previously throughout your education on the atom, okay? So, still going off of that old model, let's draw a beautiful picture of helium, and then we'll draw it the way that we've learned, okay? So take 30 seconds, I'll give you a head start. If you can, if you remember how to draw these models from back in the day or from last year, draw me a helium model if you could, and I'll jump back in about 30 seconds and draw it as well. So we have a nucleus, right? I'm going to use little p's for protons, and I'm going to use little n's for neutrons. So there's my nucleus, kind of. 2 protons, because this is helium, element number 2. So again, the element number is the number of protons. I'm going to use 2 neutrons just because I didn't give you an atomic mass, so we could have a different number of neutrons, but we'll keep it 2 for simplicity's sake. And then around the outside, we have the electrons, which I'm going to draw as E minus. Okay, and I'm going to separate those as far as I can because they're negatively charged, and we know that negative charges or like charges repel one another. So we'll split them up as far as we can away from one another. But this is probably what you've seen, what you've learned, and even last year I know that you guys went over this just a little bit in the first unit. So you did this exercise last year, and you were asked the same question last year, but let's do it one more time. What's wrong with this? Okay, if somebody wants to unmute themselves and help me out a little bit, what is wrong with this model, or what's a couple things that just aren't great with what we've just drawn? And now this is an exercise in awkwardness to see who can withstand the awkwardness the least. Hello.
So like, I mean, one of the big obvious things about these diagrams as well, they're not to scale at all. Although if you drew it to scale, it would be like, that'd be impossible. But
yeah, thanks, Sam. So yeah, the scale is all sorts of messed up, right? My nucleus here, in relation to the size of my electrons, or where the electrons are located, is all sorts of wrong. I think the example that we used last year was if you have a P at the 50-yard line of a football field, the P is the nucleus, and the stadium is where the electrons would be, or like that's the size of the atom. So yeah, the nucleus of an atom is insanely tiny, really, 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 really small in relation to like the space or the area where the electrons are. So yeah, the scale is all sorts of off. What else? Somebody else?
Protons and electrons aren't P's and E's.
Yeah, absolutely. So we have letters representing particles, right? Now, having said that, I'm not quite sure how to draw the real looking thing, and I couldn't do it anyway because I'm an atrocious artist. But yeah, absolutely, right? This is a model, and we're using letters to represent actual particles, so that's not great either. What else? How much patience does one man have? Don't be scared. You can talk. It's okay. I mean, I could stand here for 15 minutes and not do anything. Does that sound cool?
What was the question?
The question, I'm sorry, the question is what's wrong with our model? In other words, what this picture that I've drawn, it's not great. It's not a great representation of the actual atom. So what's wrong with it, or what's the problem with it?
I have one.
What's up?
It's only two-dimensional.
Yeah.
Real atoms are 3D.
Exactly. Okay. So this is a two-dimensional drawing of a three-dimensional object. That's not great. Now, again, I can't draw. I'm not a good artist, so I'm not going to draw this three-dimensionally, but you get the idea, right? Okay, so the scale's all off. We're representing particles with letters. It's not three-dimensional. There's all sorts of problems with this, right? And you learned that last year. But now let's fix that, all right? Let's go forward and let's fix a little bit of this model and give you a more modern or more accurate representation of what the atom is, all right? More specifically, we're going to talk about the electrons today, all right? The electrons are really the crux of chemistry. If we're dealing with the nucleus and protons and neutrons and things like that, that's nuclear chemistry. It's absolutely a field. It's certainly applicable and certainly something we could talk about. But at the end of the day, especially in intro chemistry or first year college chemistry, which is kind of what you're in right now, the electrons are really what we focus on. So today is going to be all about the electrons and where they are and what they do, okay? All right, so that leads us to this. There's a big wall of words, and you're more than welcome to read that, but let me give you the gist of what we're going to talk about, okay? So the model that you've been taught isn't great, but you already knew that, right? We taught you that last year. We just talked about it 2 seconds ago. It's not a great model for the actual atom. So the better model, or the more modern current model of the way that scientists represent atoms, is based off of quantum mechanics, all right? Quantum mechanics is a field of physics. It's essentially physics for really, really, really tiny things, all right? It's the physics of particles. So quantum mechanics, or the quantum mechanical model of an atom, is based off of three-dimensional calculus applied to protons, neutrons, and electrons. And yes, if that sounds horrible, it kind of is. There's a class in college that I took called physical chemistry, and it was a year-long course essentially where we used three-dimensional calculus on atoms to understand where the electrons were and how they were moving. Yeah, it's brutal. If you get to that point in your education and you are in physical chemistry in college, hang on for dear life, and best of luck as you plow through that class that is insanely difficult, and I don't hardly remember a darn thing from, but I do remember doing lots of three-dimensional calculus, and it was really tough. So anyway, that's where this model is coming from, okay? It's mathematically based. It's based in physics of particles, all right? So with that comes something called orbitals. Now, it's not a great name, and the reason why this is not a great name is because it includes the word orbit, all right? That old model of an atom that we just drew, it's also sometimes called like the solar system model of an atom, meaning like the nucleus is the sun and the electrons are like planets, right? That's not great. That's not what we want. That's not a good model of the atom. So orbitals are from quantum mechanics, all right? And these are three-dimensional three-dimensional regions around the nucleus where electrons exist. Okay, so it's not a fixed path like that solar system model. It's not a necessarily even circular or elliptical like that solar system model. But an orbital is a three-dimensional region of space around the nucleus, and that region is where the electrons are. All right. Again, there's a whole lot more I could talk about and a whole lot more I could teach you, but it does get rather complicated rather quickly. So we'll start with this, and we'll kind of build up just a little bit over this unit. All right. I'll give it another 5 seconds just to make sure everyone's got that written down, because sometimes I go too quickly. All right. Okay, so electrons don't travel in these elliptical or circular paths like we've represented with our previous drawing. They exist in orbitals, all right? There is a nice way of determining which orbital electrons are in. There are different types of these orbitals, all right? And we're going to get into that in a slide or two. Before we do that, there's something called the off-ball principle, all right? Which is, again, dead white guy, his principle. Okay, great. So as electrons are added to atoms on the periodic table, the electrons will always fill the lowest energy orbital, all right? This will make more sense later when we start having our representations. But essentially, if I have an atom and that atom has 5 electrons, if I want to add a 6th electron, the new one, or that 6th electron, will always go in the lowest energy orbital available, all right? So this principle is just saying that when you add electrons to atoms, those electrons always fill up the orbitals in order of the lowest energy first, all right? And again, that definition will hopefully make a little bit more sense as we get a little further. All right, so here are pictures of orbitals, all right? There's a whole bunch of graphs, and if you notice, these all have X, Y, Z coordinates, right? These are three-dimensional coordinate systems. So these graphs, if you look at the top one, which is red on my screen, and on your paper, you know, it's black and white, right? But so they're not great, but this is spherical, all right? This red graph here is a spherical ball-like region, and that is an orbital, all right? Again, let me just recap. An orbital is a region of space where the electrons exist, okay? So this origin, right smack dab in the center, where the X, Y, and Z axes all meet, that's your nucleus. And around that nucleus, this red spherical shape is where those electrons would exist if they exist in an S orbital. There are different types of orbitals. There are S, P, D, and F orbitals, okay? The little subscripts on the P, D, and F orbitals, ignore those completely. It's something that's not a part of this class, okay? So even though this says P subscript 0 and D subscript 0 and so on and so forth, ignore those little subscripts. It's not a part of AP Chem, okay? So there are S, P, D, and F orbitals. Those letters of these orbitals are describing the shape, all right? So S orbitals are always going to be spherical. P orbitals are always going to be this sort of, I call it like an infinity symbol, right? So like for math class, okay, kind of like that. That's the way I describe it. It's three-dimensional though, right? It's not two-dimensional. It is kind of like, it's like there's two kind of spherical regions just kind of next to each other, right? But the nucleus is still smack dab in the center, okay? So these, or this shape, represents p orbitals. If I go down to D and F orbitals, you can notice the pictures get even crazier, right? But here's the takeaway. There are different types of orbitals, and those different types of orbitals have different shapes. Orbitals always contain electrons, okay? This is a graph, right? That's why the graphing coordinates are on there, the X, Y, Z. This is actually a graph of the three-dimensional calculus that I was talking about earlier. When these scientists and these mathematicians did all this math on these particles, or on the protons, neutrons, and electrons, the calculus they did gave them this shape when they graphed it, okay? So you can think of these as like three-dimensional probability graphs, so to speak. So the electrons in an s orbital with 99% confidence will exist within that spherical region if they're in an s orbital. With 99% confidence, the electrons in a p orbital will exist within those spherical regions, okay? Again, this is getting abstract. I understand it's getting abstract. I hope you're hanging with me just a little bit. I'll recap like 14 more times before we go for the day, I promise, okay? Let's keep going. All right. So instead of writing math expressions or doing the calculus, right, because we don't want to do that. That sounds awful. We have letters to describe the shapes, all right? A sublevel or a set of s orbitals is always going to be one orbital. Orbitals come in sets, all right? If you have an s or a spherical shaped orbital, it's just a set of one. If you have p orbitals, which are like that infinity shape, come in sets of 3. D orbitals come in sets of 5, and f orbitals come in sets of 7, okay? And then I say, do you see a pattern? Yeah, of course you do, right? So s is 1, p is 3, d is 5, f is 7. In theory, if there were more orbitals beyond f, which would be called, they'd be called g orbitals, okay? If we did have g orbitals, they would come in sets of 9, right? So there's very clearly a pattern here. As we go down the different types of orbitals, we're going up the odd numbers, so to speak, or 2 more, 1, 3, 5, 7, 9 if we went further, all right? The last sentence on this slide, I need you to underline that or highlight that or star that or draw a rainbow across the top of it or a prancing unicorn over that sentence. I don't care. You need to do something that like mega draws your attention to it, okay? That absolutely needs to be like one of the main things you take away from today. You have to understand that sentence, please, okay? So do what you need to do to make sure that you realize, oh, I should probably look back at that. Each orbital can only ever hold 2 electrons, no more, okay? What does that mean? Let me go back, all right? Let me go back to my pictures from the previous slide. Each one of these graphs is a single orbital, all right? This is one orbital. This is also one orbital. And so is this, okay? So even though those graphs or their shapes are very, very different, each one represents one orbital. What that means is that I can hold only 2 electrons in any one of these orbitals, okay? Even though this f orbital down in the bottom right-hand corner has all sorts of crazy, like different spots, right? It's kind of like a cluster of like these little grapes or something, right? It's only one orbital, okay? And it can only hold 2 electrons. That's really, really important. So don't let the shape throw you off. Each one of these weird shapes down below on the F row is one orbital. It can only hold up to 2 electrons, no more. All right, so I'm gonna go through this slide really, really quickly. Wolfgang Pauli, dead white guy, okay? He's got something called the Pauli exclusion principle. This basically just says that if you have 2 electrons in one orbital, meaning, again, if I have 2 electrons within one of these graphs or in the region of space of these graphs, they have to be spinning in opposite directions, okay? It's a physics thing. Essentially, when charged particles are in motion, they generate magnetic fields. And if one of these electrons is spinning in one direction and another one is spinning in the other direction, they will generate opposite magnetic fields, and they can exist in the same region of space. Please don't worry too much about that. It's something that just needs to be said, but really it's not something that gets tested on. Long story short, if I have one electron and two electrons in the same orbital, they're spinning opposite ways, okay? P.S. Wolfgang is an awesome name, and I really missed an opportunity when I named my son. I absolutely should have gone with Wolfgang. It is just rock solid. If you are contemplating having children in your life later, I mean, you've got to keep Wolfgang somewhere near the top of the list. Great, great name. Really awesome stuff. And it needs to come back in our society. All right, I digress. Okay, orbitals. We represent these by letters and numbers, okay? So this down below is a 2p orbital, or the way we would write a 2p orbital. The 2 is talking about the energy level, okay? I'll describe how to find that tomorrow, okay? But there are different energies or different energy levels for all of the different shapes. You can have a 1s orbital, you can have a 2s orbital, 3s, 4s, 5s, 6s, and the number out front just is implying what level or the energy level of that orbital. The letter represents the shape or the type of orbital, okay? So this letter represents P, meaning the P shape for an orbital, which was this infinity symbol, the two spheres next to each other, right? That shape. When you say a p orbital, this shape should come to mind. Okay? The other thing is the letters represent the sets. Remember, if you have s, if this was 2s, that would only be one orbital. But since it's 2p, orbitals or p orbitals come in sets of 3. So when I say 2p, the p means that I really have 3 orbitals in that set, okay? And remember, each of those orbitals can hold 2 electrons. Again, I hope you're hanging with me a little bit. If I'm confusing the absolute crap out of you, I do promise that over the next couple days, it'll start to settle and make a little bit more sense slowly but surely. So please hang with me. If I'm losing you today, try to get as little bit of you out of it as you can, and it will start to click as we move forward. All right, so we're going to represent electrons in a couple different ways using this new model, which includes the orbitals, okay? You're responsible for number 1 and number 2. We're going to represent electrons by drawing orbital diagrams, and we're also going to represent our electrons through electron configurations as well. Number 3 is called quantum numbers. It's not in the AP curriculum. It's really fun stuff, but it's just not a part of the class. So it is what it is. I'm not going to teach you something you don't need. But what I want to point out is that these two, okay, these two different types show the same information. Okay, we're going to have 2 different ways of showing the same darn thing. All right, orbital diagrams and electron configurations. So we're going to go through one example of each of these, and then we'll call it a day, and I'll pick this up tomorrow with a video, okay? All right, orbital diagrams are first, okay? The key word here is diagram. Okay. That means like picture. So when you're doing an orbital diagram, you are drawing a picture of the electrons. Now, it's not a picture like a model or like the atom we drew earlier. We're going to represent the electrons a little differently in an orbital diagram. Okay, so hang with me. I have these numbers and letters, and I have these little platforms. Okay, the number and letter are showing me the energy level and the type of orbital that it's talking about. The platform is representing an orbital. You'll notice that for S, 1s and 2s, I have one platform because s orbitals come in sets of 1. Once I get to 2p, right there, the 2p orbitals come in a set of 3 because they're p orbitals. And I have 3 platforms representing each of those orbitals individually. Okay? Again, the letter is the shape and the number in the set, right? So if it's S, it's spherical, and there's only going to be 1. If it's P, it's the infinity shape, and there's going to be a set of 3 of them. All right? The number up front is the energy level. I'll talk about that tomorrow. So here we go. I want to do the orbital diagram for argon. Okay, argon is the 18th element on the periodic table. And if we're talking about its electrons, we're talking about 18 electrons. We're going to use neutral argon, 18 protons, 18 electrons. We're going to draw these electrons on the platforms. Okay, each orbital can only hold 2 electrons. 1, 2. I'm using half arrows. All right. So that's like a half of an up arrow missing, half of the little head on there, and then half of a down arrow, same thing, missing half of its little head on there. Okay. These arrows are electrons. So I have 1 up, 1 down. Up and down are talking about the spin. If you remember a couple slides ago, I talked about the about the Pauli exclusion principle. All right. And what that guy said was if electrons are in the same orbital, they're spinning opposite directions. So that's why I have 1 up and 1 down. But these arrows are the electrons. The platforms are the orbitals. Okay. So we need 18 of them. All right. So I've got 2. Let me add some more. The next 2 electrons go in the lowest energy orbital, the next lowest. And you'll notice that I kind of have this get higher and higher as it goes. That's representing higher and higher energy. So 2s is the next lowest. That's where these next 2 electrons go. Then I get to 2p. Electron 5 can go right there. But now we have a choice. Where should electron 6 go? All right. And here's the answer. For electron number 6, we're going to follow what's called Hund's rule. Again, dead white dude. All right. He's credited with saying this. When you have electrons in orbitals that are the same energy, so these 3 platforms on 2p, each one of them is an orbital, and they're all the exact same energy. Hund's rule says that we should first unpair them, meaning separate them in those 3 orbitals, and then if we're still adding more electrons, we pair them up after the fact. Okay, so this is electron 5. Electron 6 should go right there, all by itself in its own orbital, because these p orbitals are all the same energy. Electron 7 can go right there. And when I get to 8, 9, and 10, now I go back and I pair them up, like such. Okay, I've got 10 electrons in my model so far. I want to keep going. I need 18 total. I add 2 to the next lowest energy, and then I add 1, 2, 3, 4, 5, 6 to the 3p orbital to finish this off. That's a total of 18 electrons. And again, each platform is an orbital, each arrow is an electron, and this is showing a model or a diagram of where the electrons exist in an argon atom. Okay. All right, last but not least, let's do an electron configuration, and then we'll call it a day. So the order in which orbitals get filled with electrons can also be represented by an electron configuration. An electron configuration is a shorthand way of writing it out. So instead of drawing a picture, we're just going to shorthand the orbitals and the electrons through writing, okay? So this is the electron configuration for calcium. Calcium is element number 20. And let me explain what we have going on. Okay, this 1s is my orbital. The superscript of 2 is the number of electrons. Okay, so I have a 1s orbital, and it contains 2 electrons. Because again, S orbitals come in sets of 1, and each orbital can only hold 2 electrons total. I then have a 2s orbital that also contains 2 electrons. Next, I have 2p orbitals, but p orbitals come in sets of 3. So now I have 3 orbitals to fill up. And if each orbital can hold 2 electrons, that's a total of 6 electrons, so on and so forth. All right. The order of the orbitals is talked about tomorrow. So remembering or organizing 1s, 2s, 2p, 3s, 3p, 4s, so on and so forth, you'll learn tomorrow. But for today, I'm content. I'm going to leave you alone. I have a hunch I've fried your brain enough. Okay. Again, hang in there. This gets a little easier with more exposure. And truthfully, what you're responsible for is the diagram, the orbital diagrams with the platforms and the arrows, which are the electrons, and the electron configuration, which is this, a shorthand way of showing the orbitals and how many electrons they contain. Okay. So if you're not feeling it and I'm, hurting your brain, I'm all done. Have a lovely day. If you want to hang out afterwards and you have any questions, please chill and stay. Otherwise, we'll catch you guys tomorrow. Thank you.